Hello and welcome to your lecture. In this recording, we're going to go over the endocrine system. This is absolutely one of my favorite systems just because it's kind of the everything button. Remember, our two primary homeostasis regulators are the endocrine system and the nervous system. So these guys overlap a lot. They are our first line of stress responders and information dispatchers in the body. So they both concomitantly work on control mechanisms. When we look at cell communications, we already learned a few. We learned about gap junctions. Gap junctions were one of our ways that we built tissue out of cells, singular cells. We linked them together with connexicons and created this little channel that could carry fluid and particles. So we also learned about neurotransmitters when we talked in the nervous system. Now, neurotransmitters classified by structure and function. We know that they are released by neurons into the synaptic cleft, and then the postsynaptic cell hopefully will have receptors to receive the information or the command that the neurotransmitter is given. Now, in this section, we're going to go into what's called paracrine hormones or local hormones. They get secreted into the tissue rather than into a cleft. So they have, and when we talk paracrine, it's more of a local style of control. So, for example, an organ might need to self regulate and it will release a hormone just kind of for itself in the area of its anatomical location. General hormones have a more systemic effect. When we talk endocrinology, that's the study of the endocrine system, its organs, the hormones, how they function, and it is intensely intricate and complex. Again, hormones are the chemical messengers. So when I say chemical messengers, the structure of a particular hormone will deliver a particular message to a particular receptor. Now, with all of this, and we'll say this again soon in the PowerPoint, this is fascinating to me because you can have one hormone sending out a message, but it will be dependent upon the target, what the message says, and then the guidance. So I honestly think that's a giant life lesson. Okay, the deliverer of a message, it could be a general broad meaning, and it's really up to who receives the message, what the message is, and what the message will do. The endocrine organs we have to recognize are the pineal gland, which is part of your epithalamus in your brain. We studied that when we were in the nervous system. The hypothalamus, if you look at the word, it's under the thalamus. The thalamus, remember, part of the diencephalon. The hypothalamus will give direction to then the pituitary gland. And the pituitary gland, if you recall, was connected to the hypothalamic region by way of the infundibulum, which is the little stalk or stem. And then the pituitary gland itself is a little bulb. Now, the pituitary gland, recall, sat within the sella turcica of the sphenoid bone. Then we have the thyroid gland within the throat, and then the four parathyroid glands, little small glands on the backside of the thyroid gland. And we learned about some of these hormones when we were in the skeletal system because of how intimately intertwined those systems are and how it regulates serum calcium levels, both of them. The thymus gland, one of my favorite glands, bilobed gland that sits above the heart in the mediastinum. Now, this guy doesn't get a lot of airtime, or I don't feel enough airtime. It is responsible for the maturation, primarily the maturation or a stage in maturation of your T cells. And your T cells or your T lymphocytes are your viral and cancer fighters. So big deal. Then we have the adrenal glands. Adrenal glands sit on top of your kidneys. We're going to go into them more in depth in this section. The pancreas Pancreas, recall, is endocrine organ and exocrine. We'll review that shortly. It's also endocrine organ as well as digestive accessory organ. And then we have the gonads. Both female and male gender bodies have gonads, testes, and ovaries, male, female, respectively. So recall that exocrine glands will produce and secrete their chemical message by way of a duct out of a group or collection of I can't even say a group of cells. It could be a single cell producing the hormone or the message, and they will secrete that onto some type of epithelial surface or lining. So it could be the skin, but it also could be the lumen of the small intestines, for example. Where the endocrine glands, to be classified as such, they have no ducts. So they will secrete their product, and then their chemical product will be picked up by a capillary bed that will surround the endocrine organ that is doing the secretion. A couple differences within nervous system versus endocrine system. The nervous system has to be built for speed. We learned about that. So it will be faster and more specific in its target generally. Also, it adapts to long-term stimuli differently than endocrine system does or endocrine organs do. Meaning this, like you can wear a watch and your nervous system will, by way of the reticular formation, kind of desensitize itself to that stimulus to pull out the noise from the mind. Otherwise, there would be way too much going on. It would be overwhelming. Also, the endocrine organ can take up to 2 weeks to like finish what it's doing with something. So again, it lasts longer. Its stimuli can be around longer, whereas neurotransmitters have a more immediate impact and directive. This is also interesting. I mentioned the overlap of the two systems. You can have a neurotransmitter that acts or is classified as a hormone and vice versa. So we have norepinephrine is similar to that. It can act as both. We see within these systems that they can have overlapping effects. For example, norepinephrine and glucagon will both cause glycogen to break down in the liver, one being a neurotransmitter or classified as such, and one being a hormone. And then we need the systems to regulate one another. They have to talk to each other. So these chemical messages sent out by one can be received by the other. It's like they can interpret one another's language. When we talk about the endocrine system, we have to talk about that hypothalamus. Remember, it's under the thalamus or under that portion of the diencephalon, and it's responsible for regulating more of the primitive functions of our body. So water balance, thermoregulation, sex drive, and childbirth. The hypothalamus will give direction to the pituitary gland. So the pituitary gland is called the hypophysis. Now it has two divisions, has an anterior division called the adenohypophysis and a posterior division called the neurohypophysis. So within the adenohypophysis, this is actually an upgrowth of the pharynx or the throat. The posterior pituitary or neurohypophysis is actually a downgrowth of neural tissue from the brain. And it is supplied or derived from that hypothalamic region, and it will send signals via a hypothalamo-hypophyseal tract. The posterior portion of the pituitary can be noted here, and we'll say it again, is for storage. The hormones of the posterior pituitary are created in the hypothalamus, but stored in the posterior pituitary until directed to be released. Within the anterior pituitary, it has a linkage to that hypothalamus via the hypophyseal portal system, which is really like a vascular bed. So in this slide, we can see an example of that. We have the hypothalamus will secrete releasing hormones. So most of them will have an abbreviation somewhere in the nomenclature of RH or releasing hormone, but they also have a couple that are inhibiting hormones, abbreviated IH. So the 6 hypothalamic hormones that are created. We have TRH or thyroid trophin releasing hormone, CRH or corticotrophin releasing hormone, gonadotrophin releasing hormone, which is GnRH, and growth hormone releasing hormone, GHRH. And each one then will talk down to the pituitary gland to direct it to release a specific hormone. The 2 inhibitory hormones of the anterior pituitary are PIH or prolactin inhibiting hormone and somatostatin, which will inhibit the release of growth hormone from the anterior pituitary gland. Now we have to recognize oxytocin and antidiuretic hormone or ADH. They are produced again within the hypothalamus and then stored in the neurohypophysis or the posterior pituitary gland. Stimulus of the hypothalamo-hypophyseal tract will cause the release into the posterior pituitary capillaries. When we talk then, okay, so that was hypothalamic. There are 6, again, 4 stimulating, 2 inhibitory. The hypothalamus will direct then the pituitary to release whatever hormone it needs to release. The hormones that can be released from the anterior pituitary, there are 6. Follicle stimulating hormone or FSH. This will stimulate the secretion of estradiol, which is precursor to estrogen, the development of follicles, and also sperm production. So it needs to be noted that what we're talking about happens in both gender bodies. Luteinizing hormone then also stimulates ovulation, progesterone secretion, and testosterone secretion. Thyroid stimulating hormone stimulates the secretion of thyroid hormone. Adrenocorticotrophic hormone or ACTH will stimulate the adrenal glands to secrete glucocorticoids. Prolactin stimulates the mammary glands to synthesize milk and enhances secretion of testosterone by the testes. So worthy of notation here, but I'll say it again later, prolactin is responsible for the synthesis of milk, not the ejection of milk, and they are 2 different things. Growth hormone then induces the liver to produce growth stimulants, which will stimulate mitosis and cellular differentiation. When we get to that posterior pituitary, then once again, I already mentioned antidiuretic hormone. It's an antidiuretic, which will regulate or reduce urine production. So antidiuretic hormone helps retain water, which is going to have an impact on blood pressure, reduces urine volume, prevents dehydration. Oxytocin, recall, is the other neurohypophysis hormone produced in hypothalamus, stored in posterior pituitary. Oxytocin is we call it connection. I make a joke about it and say it's an ownership hormone. There is the hormone of sexual connection, but also this goes into when a mom has a baby, there's a bonding to this. So it promotes emotional bonding between a lactating mother and an infant. This is the hormone involved with milk letdown or ejection. So it can be produced, but it has to be able to be ejected. This is the hormone responsible for labor contractions. Remember, way back in, I think that was probably chapter 1, we discussed feedback loops, and we're going to review them shortly, but this is one of your positive feedback loop mechanisms. Once it's inspired, like a labor contraction starts, it will keep going and increasing. Also, oxytocin is related to sexual arousal and orgasm. So in this picture, you get a little bit of an idea. Oh, pictures, by the way, I think most of these come from McGraw Hill Education, just so we're aware of where they came from. But we can see the nuclei of the hypothalamus and how within the nuclei, remember when we have nuclei within the brain centers or central nervous system, these are collections of cell bodies. So we're going to see then collections of cell bodies within the hypothalamus that will have axons that will lead into, in this case, we're talking about the posterior pituitary. So we have two different nuclei that can regulate this. One is called a paraventricular nucleus, and one is called a supraoptic nucleus. Guess where that's close to? If you look at it, it sits right above the optic chiasm. And by design, if you think about really all of this and how if we're understanding the hypothalamus have primitive functions, and we have learned how important and valuable eyesight is and how much of our nervous system is dedicated to sight. This is kind of paramount, I think, in design and arrangement in anatomy. So remember, negative feedback loops will get a signal that all is well and they shut down a process. An example of that would be thyroid stimulating hormone. TSH would be spit out from the pituitary gland, telling the thyroid gland to release T3 and T4. Once the body has enough active T3 that's been created, then the pituitary gland will reduce its production of the TSH. That's a negative feedback loop. When we have a positive feedback loop, like oxytocin release, which will cause a contraction, the pituitary gland's like, oh, okay, we started this, we need to finish it. And this will go until there's a signal that the baby has been delivered. The pineal gland, I think we've mentioned somewhere along the line, it's one of my favorite, neatest glands. We don't know everything that it's capable of doing. Imagine that, one of those things where we have a lot to learn. So it is in that epithalamus or above or outside of the thalamic region. What this guy does is it helps synchronize physiological functions within a 24-hour circadian rhythm. This is based on light. So whether your eyes are open or not, you will have an awareness of what time of day it is, unless you screw up your internal clock. Screwing up the internal clock, which we actually do with a lot of light pollution, can cause a lot of health problems. It is responsible for synthesizing and releasing melatonin. And we need serotonin to make melatonin. By the way, it's a precursor. So also, if we have dysregulation elsewhere in the body of serotonin, this guy isn't going to work quite right. When we talk about the pineal gland, we have to mention seasonal affective disorder, which is a really real health concern that deals with severe depression when daylight goes away. Okay, so this will have something to do then with vitamin D production. Vitamin D, remember, classified as a pre-hormone, requires a lot of conversion steps to take place. And when we talk about serotonin in relation to melatonin production, there is absolutely a connection between specific kinds of light hitting the skin, the eyes, the body at large, and then getting this guy getting signaled as such. Here's a little bit more information on our thymus. Our thymus, remember, I mentioned it's endocrine. I don't think I mentioned that it's lymphatic and immune in function. And when we go into next semester talking about the lymphatic system and the immune system, we'll see the vast differences. So it is a bilobed gland, again, that sits there, maturation point for T cells that I already mentioned. It's responsible for secreting thymopoietin and thymosin. These guys stimulate the development of lymphatic organs as well as the activity of the T lymphocytes. When we get to the thyroid gland, just real quickly, this guy sits in your pharynx or near your larynx, composed of two lobes below the larynx. It's responsible for the secretion of thyroxine or T4 and triiodothyronine T3. T3 And T4 has to go through conversions to get to active T3, by the way. The thyroid gland itself won't spit out a ton of active T3. It has to go through liver, kidneys, small intestines might be involved a little bit too in that pathway, as usual, so that we can regulate metabolic rate, how each cell consumes oxygen, which is interesting. This goes into mitochondrial stuff. And I think I'll just say only that right there. Heat production, appetite, growth hormones, secretion, alertness, and quicker reflexes. So this has, although we're talking about the thyroid gland, the pituitary gland plays a large part in this, as well as hypothalamic regulation. And if a person has hypothalamic damage, that's going to contribute to this as well. Remember, we learned also then within the skeletal section a little bit about the C cells, which secrete calcitonin, and they're concerned with hypercalcemia, meaning too much calcium in the blood. So what happens when we have a blood level of calcium that's too high? We have osteoblasts or bone building cells to help lay down bone. When we talk parathyroid glands, we also touched on these in the skeletal section because of their connection with serum calcium levels. The parathyroid glands, 4 little nodules on the back of the thyroid that will secrete parathyroid hormone and PTH. This guy, like vitamin D, helps increase blood calcium levels when we see serum low. Now, vitamin D had kind of a multifaceted role, which is relevant in understanding how important vitamin D is. Anyway, back to this guy in calcium. It will promote the synthesis of calcitriol or vitamin D. So they have to work together. It increases absorption of calcium. And when we say that, we're saying within small intestines, we're saying that the kidneys won't express too much calcium. And then it's going to help with breaking down bone to put calcium into the blood so that that's regulated and circulated for other systems and organs, i.e. heart or nervous system that require it. Okay, one of my favorite things to talk about is the adrenal gland. This guy is awesome. And when we talk about the adrenal glands, this is where I like to put a plug in for something called general adaptation syndrome. General adaptation syndrome was posed by Hans Selye. I believe I'm correct in saying that. When we talk about the stresses, and these are physiological stresses, when we throw around the term stress in general speak, I think it gets convoluted. It's been taken apart. Yes, it means mental emotional stress, but that's also not separate from physiological functioning. It's all biochemistry and physiology. It's all how it all works together. Within the stress category, there are physical stresses like you trip and fall. Now that will that's also a chemical stress. That's not separate because your body has to go through some type of healing or some type of response to damaged tissue. Then we have chemical stresses, like if you're eating poison or something that you're eating is acting like a poison or a toxin on the tissues in your body, then you have to have an immune response, and it is an immune response that will do the healing. So it's like this big stress response. Also, one thing that we don't think about is temperature stresses. Hans Selye did say that temperature is a stressor because your body has got to go into immediate, homeostatic regulation. So when we leave in our society, we can leave a room that's 50 degrees and go into one that's 100 degrees. That's a stress on the body. It has to be able to instantaneously regulate. And this will come from hypothalamic regulation as well. So the adrenal gland, these are small glands that sit on the kidneys. There is an inner cortex and an inner medulla and an outer cortex. When we look at these two types of tissue, we're going to notice as we go through the rest of the body systems, when we get into next semester, that the tissue there are many organs that will have a medulla, or like I like to call it like a meaty center, and then they will have a cortical region that does a different function. Adrenal glands are cool because that inner medulla is primarily a sympathetic chain ganglion continued. And when we were in the neurology section, I went through this, but the way that the adrenal glands are controlled with the sympathetic nervous system is they have a direct wire with no synapses right to the adrenal glands because they are the chain ganglia. Now, within this, then they are responsible for producing our catecholamines or epinephrine and norepinephrine. So these are fight or flight responders. These are the neurotransmitters that are prepping the body to fight or flight. So this is sympathetic nervous system tone and control. Remember, when we are high fight or flight and we can't downregulate that tone of that system, we are chronic stress land. When we are chronic stress land, we're depleting resources. When we deplete resources, things change. We can't do things. Body goes into dysregulation. This goes back into the general adaptation syndrome. There are stages of it. When you get to a point where the body is tanked, depleted, doesn't have what it needs because it's been in chronic fight or flight, this is when this is chronic fatigue syndrome. This is adrenal fatigue and failure. It's not working. It can't work. It cannot prep you. It has nothing to prep from. So this is where we put a plug in for maintaining resources that the body requires. What are those resources? When we talk anti-stressors, we're also talking anti-inflammers, pH balancers, buffers, anything within the diet or anything that can heal damaged tissue or assist in the healing of damaged tissue is going to allow for the depletion and decrease of symptomatology. So when we get to the cortical region then of the adrenal gland, this is where the mineralocorticoids are produced. And we're going to get into that here in a second. Just another reminder, when we're in high fight or flight or high sympathetic tone, we are not digesting food. We might be eating it, but we're not digesting. And digestion has multiple phases to it. And if your body won't care. Your body won't care. It needs the nutrients, but right now it's doing an instantaneous, innate, and instinctual action. And keep in mind, I keep saying sympathetic nervous system tone, tiger is real or imagined. Doesn't have to be real time. No one else needs to know about it. It's just happening inside the body. And your body's not going to know the difference between a real tiger or an imagined tiger until you train it as such. Also, when we have high sympathetic nervous system tone, we are not urinating well, which means we are not regulating blood pressure well. We have high blood pressure, we have damaged kidneys, et cetera, et cetera. Now, back to the adrenal cortex. When we have steroid hormones produced, these are called corticosteroids or corticoids. There are 4 major steroid hormones. They are aldosterone, cortisol, androgens, and estradiol. So aldosterone helps with blood pressure regulation. Blood pressure regulation comes from primarily, not only, a little bit does come from the heart itself with a hormone produced because it's talking down to adrenal kidney regulation. So when we are working with blood pressure, it is paramount that we are investigating kidney adrenal function. When we get to cortisol, cortisol gets a bad rap. Initially, it's anti-inflammatory. When you're in chronic cortisol land, that's when it starts to not work. Once again, you're depleted. Your nutrients are depleted because you've been doing other things. It serves a role in gluconeogenesis, fat and protein catabolism. So we're breaking down fat and protein, which we're going to learn about that in metabolism next semester as well, a little bit more. And then gluconeogenesis, the production of new glucose or new ways, we can say that, because we need to repair tissue. So it does have a really profound effect. It's just, we don't want it there chronically. Androgens, this is really relevant. You've heard me say this when we are high sympathetic nervous system, high fight or flight, we are not going to be able to make babies right. This sets the libido throughout life. Okay, this is the cortex. There's a role in prenatal male development, which includes DHEA, another hormone, which other tissues convert to testosterone. So estradiol then is produced by the adrenal cortex in small quantities, but it's important after menopause for sustaining adult bone mass. When we talk about the pancreas, it's really within the upper part of the abdomen. It's an exocrine digestive gland and with endocrine cell clusters. So it does have a duct that will empty and combine with juices from the liver gallbladder complex. When I talk about upper GI line, I mean liver gallbladder pancreatic complex, because we of course we identify them separately and observe them separately, but they're so tight in their function. When you impact one, as with anything within the body, you're impacting the function of the other one. So the ducts will empty into the duodenum, which is the first part of the small intestine. Now, the endocrine clusters, this is the islets of Langerhans, pancreatic islet cells. We have beta, alpha, and delta cells, and each one has a different function. So the beta cells are the ones for producing insulin. So a type 1 diabetic will have damage to these cells. The alpha cells of the islets of Langerhans are the glucagon producers. Glucagon is the hormone that goes and helps break down glycogen when blood sugar is low. When we talk about the gonads, then let's talk about the female gender body ovary. These guys will be stimulated by FSH and LH in order to release estradiol or estrogen. Estrogen has an impact on the growth of ovaries, secondary sex organs, the widening of the pelvis, and the deposition of fat. Progesterone is also produced by the ovary in order to prep the uterus for pregnancy. Also, when we learn more about oogenesis next semester, we're going to dip into reminders of how the menstrual cycle works and ovulation and all of that neat stuff in the hormone controls. The testes in the male gender body, FSH and LH, when encapsulated within the male gender body, will stimulate the testes to release testosterone. This will develop male reproductive system in the fetus as well as the adolescent and sex drive, or at least testosterone does. And then testosterone is responsible for the sustenance of sperm production. When we talk about hormone classification, I mentioned structure and function. That's kind of always the way, right? Structure has an impact on function, and function has an impact on structure. They're not separate. That's a bilateral exchange. So steroid hormones, remember we talked about this. This is where I put my plug in for cholesterol. Is not the bad guy. He gets a bad rap. When we have high cholesterol levels within the blood, we need to do some sleuthing to see what is in disrepair. Why is the body sending out messages to pump out cholesterol in such large amounts? Steroids are derived from cholesterol. They're secreted by the gonads and the adrenal glands. This would be estrogen, progesterone, testosterone, cortisol, aldosterone, DHEA, and calcitriol. So when we have, again, I'm going to take this back into sympathetic nervous system control. We have regulation. These guys are pumped out due to high stress. We can say that. Now, remember, high stress has different categories to it. Then within hormone chemistry, we have peptides and glycoproteins. These are created from chains of amino acids. These are oxytocin, antidiuretic hormone, releasing and inhibiting hormones, and the anterior pituitary hormones that we talked about that got released. Then we have biogenic amines or monoamines. These are derived from amino acids. These guys are types of hormones that are secreted by the adrenal, pineal, and thyroid glands. So as we walk through each organ, you can kind of put them in their classes and see the hormones that they produce, their structure. This would also include epinephrine, norepinephrine, melatonin, and thyroid hormone, clearly because we mentioned pineal and thyroid glands. All hormones are made from either cholesterol or amino acids with carbohydrate added to make glycoproteins. So in order for your body to have resources to respond appropriately, deliver message, and not go into fatigue and shutdown, we need cholesterol to be available to be produced, and we need particular high quality proteins. So this is an important little map here too. When we're looking at the synthesis of a steroid hormone, it's starting from cholesterol. We're saying we're making a steroid. It's going to get converted into progesterone, and this is across the board. After that, that progesterone can be converted into either testosterone, cortisol, or aldosterone, depending on what's being called for in the body. Now, if you're high fight or flight, you're going to not worry about making testosterone. You're going to worry about making aldosterone to regulate blood pressure and cortisol to help with stress loads. If you're out of sympathetic nervous system control, not out of, but it's toned down and it's regulated and modulated by the parasympathetic tone, meaning you have stress modulators, then you're able to make testosterone, which then can be converted into estradiol with the right gender body, with the right receptors. When we talk about hormones, we've mentioned receptors, and I've said this already. The hormone stimulates only those cells that have receptors for them. So you can spit out thyroid hormone, but the cell has to have receptors. If they're not present or they're damaged, you can't hear the message. The receptor will be protein or glycoprotein in the plasma membrane. Remember way back in like chapter 1 or 2 when we were talking, maybe that was 3, chapter 3, I think maybe, or 4. We were talking about the plasma membrane and the relevancy of the proteins within that membrane. This is what we're talking about. So these receptors will turn switches on for metabolic things to happen. The receptor hormone interacts with specific hormones, and then when they're all taken up, there's a saturation point. This would be relevant in maybe like a type 2 diabetes situation too, right? So much glucose in there, insulin's being produced, but everything on every cell is taken up. There's way too much. Now what do we do? When we're talking hormones, then they have to enter the cell. We have hydrophobic and hydrophilic hormones. Hydrophobic hormones will penetrate the plasma membrane and they get to enter the nucleus. That's really cool. Thyroid hormone has to do that. They go through this, they get received, go through second messenger system, get broken down, and then they can enter the nucleus with a particular message. And that's huge. So this will also happen with estrogen, progesterone, and I already mentioned thyroid hormone. So they target genetics. That's a big deal too. That's why this system's amazing. So, excuse me, regulating production through having proper resources and then modulating nervous system control of either or all of it is paramount. So we know how we're impacting epigenetically. This is where epigenetics comes in of what's going into our body. This can take several hours or days to show the effect due to the lag of protein synthesis. Hydrophilic hormones can't penetrate into the target cell, so they must stimulate physiology indirectly. And this is an example of the use of the second messenger system. I think I mentioned that with the hydrophobic ones. I apologize. It's in the hydrophilic category. So then peptides and catecholamines are hydrophilic. So the hormone will bind to the cell surface receptor, linked to something else. It will activate G protein on the inside, which will produce cyclic AMP. This is so that it can activate or inhibit enzymes to perform various other metabolic things. So there could be synthesis reactions, secretions, changing membrane potential, stuff like that within this type of system. Okay, and that is all for this lecture. We'll see you next time.